Hi, good morning, everyone. It's my great pleasure to be here at Texas Wireless Summit and hosted by the WNCG. My first time here, but it feels like I've known these guys for years and years. We're at Qualcomm. We're great friends of WNCG, and lots of people on my team, alumni from WNCG. So I know these folks well. Also, thanks to Brian for kicking off this. I think I'm going to mostly maybe try to address in my way some of the questions that came up for Brian, and mostly also expand on some of the themes that Brian laid out. So I'm going to talk about enabling technologies. It's a sort of catch-all. It turns out that that it's a complex enough problem that a lot of variety of technologies will come together to make autonomous vehicles happen. And I've been sort of paying attention to this area for a couple of years, maybe just a little bit longer, and then kind of deeply involved in the last year or so. The work I'm going to discuss here represents the sort of output of a number of teams at Qualcomm Research, and I've listed them at the bottom. And they are people who are experts in computer vision, machine learning, GPS, sensor fusion, control, and optimization, and so on and so forth. So it's very it just makes for exciting research and exciting times ahead for us. So. It'll turn out that Brian and I coordinated reasonably well, but I might end up repeating a couple of his slides. Clearly, the way we see it, it's a coming together of connectivity and intelligence within the vehicle, and our goals are. This is the one that earlier. From my perspective, it's about the way I was seeing it. It's about saving lives. It's about saving energy, and it's about saving time. And so it's just don't pay attention to the numbers. It's nice to put up these billion and trillion numbers and so on, and they're all real in some way. They will be all real in some way. But it's all those three sort of great goals that will cause us cause this autonomy to happen. And there's this nice Vision Zero that's been around for now probably 10 years. This idea that you can get to end traffic deaths and serious injuries by 2030, and that's a great goal to have as we embark on this research. So I think the two kind of important trends that have, there's a question last night as we were discussing as to why, what is causing this to, in the last few years, suddenly the idea that this is imminent, the idea that autonomous vehicles are imminent, and what are the trends that are driving that? And I think that there's sort of two kind of significant trends that have started. This technology innovation, this idea that kind of from deep learning and computer vision advances and the amount of computation that is possible in embedded systems, sort of at the edge. And then this business model innovation that is happening where more and more people in urban environments are choosing not to own vehicles and using shared ride services and so on and so forth. And so both of those trends are forcing are causing disruption in the industry, and kind of caught in between are the current automakers and tier ones, and the idea that vehicle ownership was important and so on. So I think as these push-pull sort of proceeds, we'll see advances in autonomous driving occur. As Brian was pointing out, the amount of silicon going into vehicles even today is kind of dramatically increasing, and you can see the types of technologies that are already finding their way into vehicles. New, newer and newer new sort of multimedia experiences and infotainment and rear cameras, but now surround view cameras kind of coming along. So the idea kind of making obsolete in some way. You can kind of look through the kind of the body of the vehicle and see what's around you on the sides, behind you, and so on, so on and so forth. I've been looking at some of our demo cars from Qualcomm where basically instead of the rear view mirror, instead of the side view mirror, you have cameras that that basically eliminate blind spots, and so on. So what about autonomy itself? I think what the question came up earlier about the types of sensors, and so here's sort of a partial list. There are all kinds of radars, long range and sort of a mixture of long and short range radars, as well as potential for some types of phased array radars that can be dynamically pointed and get returns that way. LiDAR, of course, that question came up. Ultrasonic sensors for short range, and of course camera, and we'll talk a little bit more about what you can do with camera. Significant amounts of sensing that can occur with the camera. And then the way I see it, the V2X is sort of extending your horizon beyond your sensory horizon. So what you can see with camera, LiDAR and radar, but V2X can look around corners and beyond curves and so on and so forth. As well as maps and this kind of dynamic high definition maps can also give you information around corners and extended range. So you could get live feeds of stuff from other vehicles or fused maps that tell you what's going on beyond your sensory horizon. And I think so those are kind of are beyond the capabilities of how humans drive. And then I think equally important, or last but not least in this list, is precise positioning, and I'll have something to say about that. We're setting hard challenges for us, for the industry and for ourselves, to provide precise positioning, 10 centimeter accuracy or better. Okay, so it's going in and out. Yeah, sorry. Okay, so that's better. Yeah. So let me expand on. So it's what that translates into, what that set of sensors translates into, and that set of goals of is a variety of algorithms that are able to combine camera, radar, ultrasound, LiDAR, stuff that you get from communications from V2X and so on. And then on the positioning side, the GPS, GNSS, the inertial sensors, camera, and high definition maps. And what we take all that is we design algorithms, kind of sensor fusion, and address and sort of try to understand what I'm referring to here as a road world model, a model of what the road world looks like. This is a term that I like, sort of the idea that your world is this road and what's going on in that and around that and so on. And so the three pieces of the puzzle, I like to think, is perception, positioning, and path planning. So it's nice. You can remember it. So perception is kind of understanding what's around you and what you see, both from camera, but as well as other sensors. Positioning is precisely knowing where you are in this perceived space, and then planning is planning for your trajectory, but as well as understanding the trajectories of all the dynamic players around you. And so our estimate is, and this who knows, we'll see how these, but our estimate is that this sets up a nice challenge for us as Qualcomm, that basically you have to deliver maybe 100x the performance compared to smartphones in terms of data movement, in terms of just raw compute power, because of all this sensor processing and machine learning, path planning, etc. But you still have to accomplish this within a power slash thermal budget that is not like, you're not allowed to go 100x on that. And so that kind of automatically tells us that we'll be doing hardware accelerators, as well as data movement in device in some smart, efficient manner. And so that's basically, and you can't, you have to do this reliably, robustly, kind of eliminate failures and so on and so forth. So I think you have to worry about security and functional safety, which means you have to design in fault tolerance and design in sort of all kinds of robustness, accuracy in timing, and so on and so forth. And then with all this complexity into an embedded platform, we better have tools and ways and OSs that allow you to kind of program these environments. So here's stuff that here's sort of kind of what's happening. What you see whenever we're talking about autonomous driving. So you take kind of deep learning models or deep learning and apply it to things like vehicle detection and so on and so forth. And so we've been doing some of these things, and the advances keep happening. The types of models that are deep learning models that are available. So this is something called it's kind of an interesting thing, because it's kind of what's called single shot multi-box. So it's somewhat challenging. Usually you've seen the first set of things that happened with deep learning were the idea that you could kind of detect what's in a scene. So you would say it's a car. But here the goal is more sophisticated. You want to know every car, and so in this case it's every car. You can kind of design networks for other things that you want to detect. But that's kind of, I mean, this is complex. It's not. It's complex to kind of develop the network. It's complex to run. It's you have to kind of work hard to improve the efficiency of such a network to run on device and so on and so forth. So those are things that we've been working on. This is. You can see, you can get to more and more sophisticated. So if you want to get to a road world model, it may not be sufficient to look at to know that there are cars in there, but you want to know all the players and all the objects, so you know where the road is and so on. So this is something called semantic segmentation, and in this case, with one network, we're trying to kind of crudely get to the boundaries of a variety of these, 12 different categories. So in this, you can see it's again a deep learning based network with convolutional deconvolution, and you're able to, it's sometimes referred to as pixel labeling. So every pixel or every kind of coarse pixel is labeled as an object. And so, and this one, again, we've been working on optimizing, and this is running, for example, on one of our current Snapdragon 820 GPUs at about 8 frames a second. So not necessarily 30 frames a second, but we're able to get to, this is about 120 milliseconds per frame. And so there's more, there's a bunch of more optimizations possible if we needed to go to 30 frames a second, this is frame by frame, so you could do processing that tracks and so on and so forth. So so that's just a flavor of the types of deep learning, the types of abilities that deep learning gives us in our toolbox, so we can kind of get to start doing the perception piece of autonomous driving. Now, as I mentioned, the kind of we have our vision zero as our guiding light. So we need to get to using this autonomy brain. But how are we there? Can we get there pretty fast? Well, I think again, Brian alluded to this. I think there are really fantastic breakthroughs happening in deep learning. It's the richest kind of community right now in terms of what's occurring day by day. It's just fun to track what others are doing and try to learn from them. And so breakthroughs are happening, but artificial intelligence, I think, I believe, remains a tricky problem. And again, Brian alluded to this. Basically, I think doing what humans are able to do when we drive with just our eyes is that our brains are able to kind of learn a lot from simple examples. But deep learning has ways to go to accomplish that aspect of it. And so, kind of doing, I've seen talks where people are kind of looking at just when you have kind of mergers at exits and so on and so forth, and knowing whether somebody late is going to pull in or not. We humans figure it out, and I think these are the kinds of problems that autonomous vehicles or this kind of deep learning brains are going to struggle. And that may be a reason why you kind of isolate them for some time, because humans will do funny things which this autonomy brain may struggle to deal with. So we'll see. But those are the reasons. I think we're doing breakthroughs in understanding scenes and so on and so forth. But understanding intentions and predicting and so on and so forth, it may take a bit longer. That's my view. So what we do is instead of just leaving you kind of high and dry and say, go, here's the autonomy brain, go drive yourself. I think we're kind of giving the autonomy brain crutches by giving it a lot more stuff. So we give them this precise positioning, which humans don't have. We give HD maps. We provide V2X so you can look around corners, look far away. Maybe, in fact, more than that, maybe V2X actually gives you intention. So you basically, vehicles are communicating intention to each other, saying, I'm going to merge, I'm going to turn, and so on and so forth. So I think those crutches will help us get to autonomy. So that's sort of my view on how this may turn out or may evolve. So I'm going to switch to the two things I mentioned on the previous slide. So talk a little bit about positioning, and then talk a little bit more about V2X. So for positioning, our approach is to kind of get to, or our goal is to get to kind of decimeter accuracy at some 95th percentile, or less than meter accuracy at 95th percentile. And the method is to combine GPS GNSS with, firstly with axle and gyro, which kind of allows you to do dead reckoning, and then advance that dead reckoning by looking at camera features. So what is called visual odometry. So you combine features that you detect in the camera scene, you track them frame by frame, you use inertial sensors, and you use tracking with them, and you fuse all this, and it allows you to correct for losses in the GPS GNSS signal, or more importantly, multipath from GPS GNSS. And in particular, I've listed here using the GPS GNSS pseudo range, and then visual inertial odometry, and I have a sort of a demo or a video of what we've accomplished so far. So in this video here, on the right is kind of a Google Maps view of of the world, and in the in the left part of the scene is the camera view, the front-facing camera view. And on the right, the red dots here are differential GPS, and the blue reflects our fusion result, and green is ground truth GPS from a more expensive, from a $50,000 GPS IMU sitting in the trunk of the car. So I think the main sort of takeaway is that GPS is basically challenged when you approach buildings and you get multipath. And whenever you're around buildings, even in a pretty, even in a fairly, this is a fairly open, this is the New Jersey office of Qualcomm research. And it's fairly open. There's parking lots and a few buildings. And yet you can kind of help GPS even in this situation, even in this somewhat benign situation. And what we've been doing is working on more, this is from a few months ago, and we're continuing to kind of work on more typical urban, suburban driving conditions. Anyway, for the most recent results, here's some plots. And so, we have this kind of goal for 3 meter at 95th percentile accuracy in this technology with pseudo range and visual inertial odometry in mixed suburban urban driving, and this is the basic GPS plus dead reckoning with inertial is commercially available now. That gets you not this level of accuracy. You combine it with visual odometry, and we're hoping that in a year or so, this level of accuracy can be available commercially. The next thing is high definition maps. And so high definition maps, there was some discussion earlier, the low end of what is needed is basically semantic information. That's the kilobytes per kilometer type of thing, where basically it tells you what is this lane, how many lanes are there, which is exit, how many exit lanes, and whether it's one way, and so on and so forth. So that's one level of information in high definition maps. For autonomous driving, a lot more information with precise localization of features and so on can be available. So you could have precise localization of traffic signs on the highway, and that can help you correct or fix, get you to this decimeter level, lane level, lateral accuracy in the lane by fixing to visible signs in the camera, by triangulation to visible. So that's another level of information available in high definition maps. And so in this case, what you would do is the way I described earlier, you would take this GPS, GNSS, and then visual inertial odometry, and then you would also fuse with map features, with localization information that is available in the high definition map. And then not mentioned here is you can actually update those maps constantly, and that can be basically done in the same way. So I have in a second I'll talk about that. So so how do you do localization with map fusion? Basically, you can have more deep learning networks, which in this particular case, if you look up there, the sign corners, the corners of the signs are being detected. So there's a new kind of, instead of doing semantic segmentation, I'm doing this convolution deconvolution, but my output of the deep learning network is just the corners of those signs, and that allows me to, if I knew the GPS coordinates of those corners, I could localize myself. And then similarly, if I could know the GPS coordinates of the lanes, just in some functional representation, I can do localization with respect to those lanes in terms of lateral error and so on and so forth. So that's so this is not a LiDAR level 3D representation of the It's just very, very simple. You added localization information to the high definition maps for allowing your own localization. So so there's sort of two pieces to the puzzle in this case. There's map fusion. You do precise positioning by having the location or the precise position of signs and lanes, but equally you can kind of feed that information back into a map, and so that's sort of the other part. Basically, there is no need to send out LiDAR equipped expensive GPS equipped vehicles out to do mapping, because you can create these maps from thousands of trajectories captured by commercial grade cameras and GPS equipped vehicles who ship their detected sign and lane information. And you can, so this is a very interesting research topic that we've been working on. Basically how you can combine thousands of trajectories and do bundle adjustment in the cloud to create high definition maps for localization. Okay, so switching gears, again, we'll talk about next thing is positioning. So the way they're really clearly related in my mind is that V2X is going to be key to autonomous driving, but V2X becomes irreplaceable or really, really useful when you have precise positioning. It's really, you know, if you really needed to rely on V2X to avoid collisions, let's say at intersections or corners, you really want to know where the precise position of the vehicles that are communicating this, as well as speeds and Dopplers and so on and so forth. So it's the combination of positioning and V2X that makes it irreplaceable for autonomous driving. And so, so basically, again, it's it can be used to improve the efficiency on the roadways as well as to improve the safety. So, you know, all those, all three of our saves lives, saves energy, and saves time. So all three of those are enabled by the combination of V2X and positioning. And so here's sort of the bunch of use cases that we've been. This is a subset of the 50 or so that people have talked about of how V2X actually enables first enables driver safety and then eventually autonomy. And so there are obvious things like do not pass, and then, you know, looking around blind intersection, sort of looking far ahead at cues, looking and kind of getting information about curve speed, but then more interestingly, creating these truck or car platoons on highways, which V2X can enable very nicely, alerts for other problem areas. Something that Constantly mentioned about discovering parking and charging locations and so on and so forth. So all of those could be enabled nicely by V2X. Here's a couple of examples that I want to highlight. One is about just being able to, and so this could be V2I or V2X, but generally the idea that you can both crowdsource maps as well as download, and that can be very, very dynamic. So, you know, a new hazard on the road can be reported and added to maps so that vehicles that are behind you can be made aware. Kind of complex intersection management where you're communicating with other vehicles as well as communicating with road furniture like traffic lights and signs, and they're all telling you something. They're telling you speeds and dynamically changing information on traffic on highways and intersections and so on. And then finally, more sophisticated kind of collaborative sensing. So you can kind of fuse the sensor feeds from multiple sets of vehicles. This could be to enhance your GPS position, or it could be to enhance your perception by eliminating different types of occlusion that occur on cameras and so on and so forth. So you can kind of, you know, if you to kind of satisfy Bob's desire for gigabit requirements on highways with millimeter waves, I think there's stuff that that that'll enable higher and higher levels of autonomy and sensing. So I think that basically brings me to the end. My sort of takeaways for you are that basically we're designing this next generation compute platform. The smartphone, set the current generation of compute and complexity. I think the next generation of compute, complexity, embedded compute at the edge will be set by autonomous driving. So we talked about that. But it won't happen just by us doing compute, by us doing heavy compute. And so we must complement the brain with rich, diverse sensors, including LiDAR, radar, V2X, and then also complement or supplement it with precise positioning and high definition maps. So thank you for your attention.
Thank you, Sanjiv. That was instructive. I especially like that you recognize that maybe we won't get to deep artificial intelligence anytime soon, and so let's go ahead and use the crutches, the different sensors that you were talking about. Makes sense to me, too. I mean, humans drive in one way. We don't necessarily have to build cars that drive in the same way. Humans play chess in one way. We don't necessarily have to assume that artificial intelligence will play chess in the same way.
Yeah, that's well put. I agree. Yeah, thanks.
What about weather? So a lot of your techniques depend on visual navigation, visual odometry. How do you deal with poor weather? Here in Texas, we get fairly torrential rainstorms, but up north, they get snow, sleet.
So I think that's why I think this diverse sensor set, I think we must choose sensors that fail differently under different conditions, which is why I am a kind of big fan of advances in radar, because radar fails differently from light. And so I feel like, really sophisticated radar will be a part of the answer on this. Communication will be a part of the answer. Basically, if you can capture more information that is not visible to you and communicate it further and so on. Yeah. So I think that diversity of sensors is the key, and there's a long way to go in us understanding how these things will all come together. And
Sure. I've got a question about this diversity of sensors, because what I find interesting is that each one of them is pushing essentially to the limit of what's available today. Deep learning is pushing computation to the limit. Even storing these HD maps, similarly for inexpensive storage, is pushing us to the limit, and of course with communication, if I wanted to do that. And what's interesting is that there's a trade-off. I mean, you're advocating the fact that these can complement each other, but there's a trade-off. So instead of bounding boxes, if I had communication, as you said, maybe that would make that task easier. And I'm wondering, looking forward, I can imagine that there are going to be big players that want to develop infrastructure for V2X, or players that want to develop HD maps as part of a business strategy, or players that want to invest more in communication technology. So how do you think these will play out, or let me ask a more specific question, which is, where do we position, or how do we balance this tension? Because investing too much in one direction may be difficult given what ends up developing, and it's, I guess, from my vantage point at least, I have no clue what really will take the lead.
I was afraid, you had this long preamble, and I was wondering where this question was going to go. So I was just, because I think, no, seriously, because I feel, I don't think we know. I think we need to push all these, and perhaps all of them will be needed. I think it's not, I don't believe that it'll be that some of them are just not. I think all of them are going to play a role, in my opinion. I think it's a hard enough problem that it won't get solved by kind of ignoring some of these technologies and so on. So we'll push the envelope on. So I mean, as I said, so we took some of these deep learning networks that were first done for these problems, and we were able to compress them by a factor of 100, let's say, in just size of network, because we decided that it was worthwhile getting it on a smartphone chip that we can put out there, and it was possible. So, I mean, all these technologies will sort of push to the edge. Some may or may not, so again, just fundamentally physics-wise, between phased array radar and LiDAR, we have to see what becomes real in the sort of at the right cost point and so on and so forth. Another thing to keep in mind is that whatever we're thinking as cost points may also, it may turn out that we can afford to spend more if we save enough lives, save enough energy.
And especially if it's enmeshed in fleet vehicles, because you can
That's
pay
right.
more for fleet vehicles. Let's turn this over to the audience. Robert?
As I'm sitting in the front, I get priority in asking questions. So on the V2X side, I mean, how do you reconcile that? You're saying that people keep cars 10 to 15 years, but we keep our smartphones a couple years, and the infrastructure and the base stations is probably somewhere between the two. So, I mean, how do you reconcile this? How is the V2X technology going to be upgraded in the cars? Are the base stations going to keep the same technology for years and years? What do you think?
I think it'll take time to get V2X into cars. It's also interesting to think about kind of aftermarket installations in cars that may be pretty useful. I think getting to 100% penetration of V2X is maybe not needed. Maybe you can, I think there's some studies that we've been doing that once you get past 40% or something, it gets very, very interesting that you can actually start getting information that's useful. So maybe there'll be enough incentive if we can come up with interesting incentives for V2X equipped cars, and maybe some cities start deploying some infrastructure, and that allows you to speed through intersections or something. And so maybe there are some interesting ideas as to how to get penetration up faster.
The V2X units would fly off the shelf if you can go right through intersections. We've got a question up here.
Hi, Sanjiv. A question on V2X again. I mean, in a sense, there's a quantum difference between, say, level 4 full autonomous and ADAS, which everybody is talking about today and which people are developing. And in V2X, you can't rely on cars being there, people being there, or infrastructure being there. So the car has to have the capability in a full autonomous to be able to do without it. So in that sense, V2X is kind of wasteful, because you've got to design the car assuming it won't be there if you're going to be fully autonomous. So it makes more sense actually in the ADAS case, where you can take advantage of whatever is there, and you may or may not get it.
Absolutely. I think it's obvious that when you have a technology that works just when you have it, and that is why you're starting to see some of these technologies already getting commercialized. Lane keeping is an example. And so that will happen. I think to some extent, the benefits of V2X, as we said, come when enough infrastructure and enough vehicles have the technology. And I think that's why automakers, have been talking about getting a mandate so that it starts happening, and then you start seeing the benefits. So I think you need those mandates to kind of get V2X going.
Lakshay?
Yeah, so my question was, like, when you were talking about precise positioning, you had like nice error bounds, like 95 percentile error of 10 centimeter, and you had some really nice results on deep learning networks, like labeling stuff. But are there any results, or are there any research efforts going on that provide similar error bounds for deep learning networks, like the errors they are making? Is there a percentage bound on those errors, or the type of errors, or how big the errors can be?
Yeah, I think what I was showing I was hardly showing results. I was mostly telling you what our targets are in accuracy requirements. I showed you one result, I think. And similarly in deep learning, I think it's on for example, labeling vehicles and so on. I think, again, we have results. We know what kinds of accuracy are achievable. You need similar, high reliability. What brings you, it'll be kind of multiple frames, and then combining with other other sensors that will allow you to get high reliability. And so for example, there are scenarios, interesting scenarios where sometimes deep learning fails on a certain kind of, let's say, certain kind of position of a vehicle and so on, but radar would give you kind of information about its speed and the size of the object, and that when you fuse with radar, you may improve the reliability. So the target is to have, really, really high reliability, so you can kind of drive on that road and not run into things.
Do you often make classification errors with your semantic segmentation? Do you end up classifying little old ladies in wheelchairs as golf carts?
I'm sure that's true. I think this is that was intended to show the power of what a network that is running on a current generation Snapdragon can do. It just shows. This is the way I put it. I think before we started doing the semantic segmentation work, I didn't believe that was possible. I thought pixel labeling was a kind of a vague goal, and then suddenly we see that it can be done already at 8 frames per second on a smartphone.
Do you believe that NVIDIA's vision of a massive supercomputer on the car is required, or do you think, and they're looking at something that right now is running about 250 watts. What about Qualcomm's vision? Is that more like 5, 10 watts, or is it a large fraction of the energy budget of the car?
I think we're all converging in the same direction. I think 250 watts is off, and 5 watts may not be enough. So I think we're getting somewhere. We'll find that right spot that we can bear in all these, in terms of, not just in terms of the energy, but just kind of managing the thermal envelope. I don't know if you want fans cooling this stuff, so and then these things are sitting in trunks of vehicles, or even worse, and so they're not cooled very well, and so on and so forth. So I think we need to get to 5, 10 watts per ECU or per chip or something.
Just looking at the way humans evolved, our brains are quite large and take up a lot of our energy every day. So if cars are evolved that way, boy, will the motor will be replaced by the big brain that you talked about.
Yeah.
Thank you, Sanjiv, for this wonderful speech, and we'll look forward to meeting with you afterward and chatting about it.
Great, thanks. It's a pleasure to be at WNCG.